This is a summary video. And what I want to do is begin by reviewing what we saw in previous weeks. In week 4, we did grid approximation. And last week, week 5, we looked at conjugate pairs as ways of getting our goal, which is the posterior distribution of theta, the Bernoulli binomial parameter. And these guys work okay, except they don't work very well when there are multiple parameters. So eventually we're going to need something different from these guys. And the basic problem we confront is if we look at Bayes' theorem, the challenge comes in calculating the denominator. So how are we going to deal with that challenge? Well, the denominator is a constant. And that creates a possibility that what we can do is just ignore this constant. Ignore this constant. Just calculate this bit. And maybe it will work if we got some mechanism for taking random samples of this guy here. So when we think about random samples, earlier on we considered random soil samples that might be taken in two different ways. GPS randomly selecting locations in the field from which we would withdraw our soil samples, or an alternative approach where we go on a random walk. We start here, another one here, pump in some new coordinates here, another new set of coordinates here. We go on this random walk that we can think of as a Markov chain Monte Carlo approach, and that's what we're going to do. So we saw some different examples of this random walk Markov chain Monte Carlo, and the first was with our wandering politician that wanted to visit islands proportional to their population sizes. And the algorithm that was used was, if you think about the population of some proposed island that the politician might move to, as opposed to the population of the current island on which the politician currently stood, well, if that ratio was greater than 1, then they moved. If it was less than 1, well, maybe they moved, maybe they didn't move, but the probability of moving was proportional to this ratio. And so the politician implemented this algorithm, and as it turned out, there actually were 5 islands. And at each step in this process, they would tally the island that they were currently on, and ultimately that would achieve the objective in the sense that if one were to plot the number of visits against population size for the 5 islands, one would find indeed that the number of visits was proportional to the population size. And so what we have with the politician is essentially just a proof of principle or proof of concept that says, okay, maybe it is feasible to do something like this implemented with a random walk, and perhaps it'll work. So then we moved on to something slightly more realistic, where we applied Metropolis algorithm to the Bernoulli binomial parameter theta. And so what happens in this case is that we take a ratio, once again, the probability of theta proposed divided by probability of theta current. And if it's greater than 1, then we accept the proposed. In fact, in other words, we move or accept the proposed. If it's less than 1, well, we may stay on the current. We may accept the proposed. Whether or not we move is proportional to this ratio. So what happens is that we actually wind up with a chain of outcomes. So if we implement this process through thousands of iterations, what we get are our values of theta. We can think of those as theta current, as opposed to on the horizontal axis, we've got iteration, and we have a random walk like this, and then we just aggregate all these values, and that gives us the posterior distribution. Now, one of the issues that arises is, how do we calculate theta proposed? And we get that by taking theta current and adding to it some small amount delta theta, where this is taken randomly from a normal distribution with mean 0 and standard deviation sigma. And what we saw was that the choice of sigma, which is something we would have to decide upon, was not trivial, and that would affect the efficiency of sampling. And then lastly, we moved on to Gibbs sampling. And the notion with Gibbs sampling was it was going to be a lot more efficient if there were multiple parameters. So for example, instead of having just theta, we might have theta 1 and theta 2. So under those sort of situations, what we really need to focus on is getting the joint distributions, the posterior joint distributions, when we've got multiple parameters. Now, the example went over in the last video assumed that we were interested in the joint distribution of 3 parameters, theta 1, theta 2, and theta 3, and we began with the assumption that it was possible to calculate the probability of theta 1 given theta 2, theta 3, and the data. It was possible to calculate probability of theta 2 given theta 1, theta 3, the data, and the probability of theta 3 given theta 1, theta 2, and the data. So in the case of Gibbs sampling, we had a different way of going on our random walk. We would initialize theta 1, theta 2, theta 3. I'll just put a 1 up here as an index to indicate that it's the first value. And as long as we can know these conditional distributions, and how we know these, I must confess, is a bit of a mystery to me, but assuming that we knew these, then what we'd be able to do is calculate the probability of some new value of theta 1 given the initial values of theta 2, theta 3, and the data. And then what we could do in the next step is we get the probability of a new value of theta 2 conditional upon this guy right here, and theta 3 and the data. And finally, we get an updated value of theta 3 given the second value of theta 1 and the second value of theta 2 and the data. And so at the end of this step, we would have a joint distribution of theta 1, theta 2, and theta 3. And if we repeated this through thousands of iterations, we'd eventually get the joint posterior for theta 1, theta 2, theta 3. And so we've covered a lot of ground in this week, and there's a lot of details that you may find a bit confusing. The whole idea, however, is to see the big picture. And the reason is that in the future, we'll be doing JAGS, which stands for just another Gibbs sampler, and some understanding of the random walk, Markov chain, Monte Carlo process is important both in understanding how to implement JAGS, but also how to interpret the results that come from JAGS.